Okay. Hi, everybody. Welcome back. Hello. Let's take a minute to settle in here. I literally need a transition after all that. So let's just settle in. Did I hit record on that? Would you check?
Yes, you're good to go.
Thank you so much. All right. Just closing your eyes and maybe just focusing on our breath. Just becoming aware of it. Seeing what happens. It made Michael appear. Maybe coming into touch with the way your body's feeling when you're noticing that. Whatever you're feeling, just telling yourself it's okay. It's okay to be happy. It's okay to be sad. It's okay to feel completely numb. Just visualize giving yourself a big hug. Or your favorite person giving you a big hug. Whatever works best for you. Let's come on back. Got some stuff to discuss. Had like an epiphany of some kind. And if you've been in one of my classes in the last year, this is going to sound familiar. I would like to not have exams, even though they're on the syllabus. How do you all feel about that? Yeah. It's like, because what I'm thinking, because if we do an exam, I mean, so there's two ways to go with this. And if you have any objections to this and you don't feel comfortable saying that in class, please email me and just let me know if you're uncomfortable with any of this, because the syllabus is the syllabus. But what I would like to do is either there's like 40% of your grade was supposed to be exams, but the homework is so involved, and if I give you an exam, it's going to be a take-home exam, which is a homework assignment, right? And then we have to spend a bunch of time, we lose time moving forward. And so what I was thinking is we have two ways to go with this if this is what we want to do. And I'll create a poll and we can take a vote. But either take your two best homeworks and make those the exam scores so that you've got that best homework amplified significantly, or just everything is just homework, right? So each homework would still count kind of relative to its proportion, but you want to think about that a little bit? Okay, I'll send out a poll. I'll do like a little poll, an informal poll, and just to get your feedback so that everybody feels comfortable doing it. I think I'm just moving away from exams, especially in my upper level classes. It's just a lot of stress for everybody, except me. It doesn't really create any stress for me, but it's definitely stress for you, and it seems antithetical to what we want to accomplish in here. So and then maybe the final homework will be substantial and count a larger proportion than other homeworks. But I wanted to start off today. Well, first off, I didn't give you a new assignment, right? Okay. I kind of realized that yesterday. So let me do that. I want to actually look at a paper that was published Oh, jeez, I forgot to put the credits on here, but I'll get them to you. I want to go through a different proof of the Bolzano-Weierstrass theorem that we already talked about. We have a proof, but before I do that, let me get you an assignment. So next assignment, I don't even know what homework number this is. 5? Is that it? Oh, good Lord. All right, so homework 5. It's not happening with that pen. This is cool, and I knew, you know, even though I was sad, I knew that once I got here and started hanging out with you all, that I would end up feeling better. True. So, 252, 255, 261, 262, 264, 265. And then what do we, how about we say next Wednesday for like a tentative due date? Give it a shot, see how it goes. So do next Wednesday, whatever day that is. All right, so that's probably no questions. That would seem right. So let's take a look at this proof together. And let's actually let's first look at the result that we want to. Where did I put my cool pen? Did I literally lose it already? So the Bolzano-Weierstrass theorem. I think they have, yeah, nice statement of it here. So Bolzano-Weierstrass says that every bounded sequence has a convergent subsequence. And we talked a little bit about the basic idea of why this is so. Let me go through the quick proof that's in the book. I'm not going to do the details of it, but the general idea so that you understand it. So the book proof, and this is a classic proof, it's not just theirs. This is one of the major ways to do it. Uses the nested interval property. And the basic idea is this: if you've got the sequence x sub n, and you know it's bounded, I'm just putting those things up like so. We've got a sequence, it's bounded. That means it lives between m and minus m, so all of the points are inside of here. That boundedness is absolutely essential because the nature of the proof goes like this. Cut this interval in half. In one of these two halves, there have to be infinitely many points. Do you remember me talking this through? So you pick the side that has infinitely many points, and I'll just use infinity as a symbol, not representing a quantity, but representing the infinite side. And then, does everybody understand that basic argument though? That if I cut this in half, one of the two halves has to have infinitely many points. Because if neither do, there couldn't be infinitely many points. If it's finite and finite, you got finite. So to get an infinite collection, one of these halves has the infinite part. They might both have infinite collections in them, that's okay. So I cut the infinite side in half. Again, one of these two halves must have an infinite number of points in it. So let's say it's this one. I cut that in half, and one of those halves has infinitely many, and we repeat this game over and over again. And what we end up with is a sequence of closed intervals that are nested. And that's how we get them, by constantly choosing the half of the previous interval that contains infinitely many points. So we get this sequence of nested intervals, I sub n, and they're nested like this. And that's a very strict inclusion, in fact, because this one's half the size of this one. And so we know that there exists some x in their intersection by the nested interval property. And then we just have to produce the subsequence. And the subsequence is produced by, at every stage of the game, grabbing one of the points in the current interval. So when I went here and I said, okay, let's cut this in half, got an infinite part here, let's say that's x1. And then I realized, oh wait, the infinite half's over here for the next one, so we cut that in half, pick somebody out of there, there's x2, and then in each one of these intervals, just simply pick any representative you want. And in that way, what you're gonna get, and you can see the neighborhood around it is shrinking. So we get this x of n must converge to x. So that's the nature of the classic proof. But this is a new proof. I think it came out maybe in the last decade, which is, for math, that's pretty damn new, right? Like that's like fresh to your door. So let's take a look at what they've got here. And it's got a few ideas that we're going to have to talk about together. But I thought it'd be fun to do this. So they have this little intro. They state the theorem on the first page, and then talk about some classic approaches, this being one of them. In fact, you can see it right there. They call it Cantor's intersection theorem. That's the nested interval property for us. And they use that, and then there's another one that's really counterintuitive using these things called peaks. So I thought, let's see what they got here. So they actually have a slightly modified version of it that I want to talk about, and it's going to lead us into some ideas that are in the next section. So look at their version 2. So this is version 1. Version 2 says the following, that every bounded infinite set of real numbers has a limit point. And that's the phrase that's new. So I want to talk about that because it will become important to us at some point. Oh boy, it's hot. I tried to dress up nice today too. Put on this nice sweater. My wife was like, whoa, look at you. I was like, yeah, look at me. Now she knew that this couldn't last. Oh my God. There's a pickle. This is like great. I don't know what just happened, but I just found there's like a pickle. A little pickle button on my bag. What the hell? That's pretty cool. That's pretty fucking cool. All right. Sorry, guys. Welcome back to class with Dr. T. All right. There we go. So let's talk about what a limit point is. So definition. We say x is a limit point of a set S if, and I mean this is going to have a new term in it, but every punctured neighborhood of x contains points of S. So let me let you get that down. Limit point is the thing we're defining here. A punctured neighborhood is just like this. So a punctured neighborhood, let's talk about what that is. That's just simply an open neighborhood around the point, so an open interval, an epsilon neighborhood around it, with the center point removed. So a punctured neighborhood around x would be x minus epsilon to x plus epsilon minus the actual point x. So it looks like this. Take your x, remove the center, and then here's x minus epsilon, here's x plus epsilon. And imagine those are the same size, of course. Kind of a different idea for us. And notice here it says every. So that means no matter how tiny epsilon is, there's still points of S inside there. We've seen this idea a lot. It's kind of like the soup idea, but let's take a look at a few examples. So what are the limit points of, and let's just do a couple examples here. So the first one, just the open interval 0 to 1. Straightforward. We'll draw a little picture. Here's 0. Here's 1. Set it up. So the limit points of this set are going to be all the points whose punctured neighborhoods touch this set. So for example, here's not a limit point. Any point to the right here. If I take a point x to the right, there's a lot of open intervals around that point that don't touch the set. So nothing to the right of 1 could possibly work. Nothing to the left of 0 could possibly work. It doesn't touch the set for lots of intervals. But when we get close, like we say 1 here, so if I let x equal 1, notice that every interval around 1, even not including 1, if I take the point 1 out, so I look at the punctured intervals around 1, all of those spill into S on the left side. So here is intersection right here. Does that make sense that no matter how small that interval is going to be, if it's centered here at 1, that left side will spill in? So we have 1 as a limit point. Any other limit points you can observe? What's that? Did somebody say 2? That's good. I'm glad nobody said 2. Okay, 0, 0, definitely, yes. So 0 is also a limit point because if I look at 0 and take an open neighborhood around it that's punctured, it spills into that right side. So again, here, 0 is a limit point. Any other limit points here? Michael?
Feels like the whole rest of the interval.
The whole damn thing, right? So the whole rest of this thing, let's take a look at it. So okay, again, here's 0 or 1. Here's 0. Got this stuff. If I take some x inside here, remove the point itself, but then look at epsilon neighborhoods. So here's plus epsilon, here's minus epsilon. No matter how tiny that epsilon is, you're touching stuff in S. So, in fact, the limit points are the closed interval. The collection of all limit points is closed interval 0 to 1. And you can think of a limit point as there's a sequence of points who have that point as its limit. A sequence of points in the set that have that point as a limit. Kind of why the term is. Let me ask you this. Here's a set. What are the limit points? That's a discrete set. What are the limit points there? Kind of fun here. Now we're getting warmed up. What's that?
Does it not have it?
Yeah, why do you say that? No, I agree.
Because unless you include like the number that is closest to 1 without being 1, which is not a real thing.
Not in our math, yeah.
Not the math we're using, then any point you get, I can give a point that is in between them.
Yeah, exactly. Yeah, exactly. So take a look. None of these. There are no limit points here. To have a limit point, you need to have sequences, infinite sequences of points getting clustered together, getting closer together. No limit points here because take the closed interval around 0. That goes to 1/2 and -1/2. That doesn't touch the set at all. And you can't take the center point. That's why we say punctured neighborhoods. So the point where the interval is centered doesn't count as an intersection. So there's no limit points here. What about one last one? Different kind of infinity than the first one. think the limit points are here? Are any of the points in the set itself limit points? No, right? Because no matter how tiny these get together, no matter how close they are, there's an interval around each of these little points that doesn't intersect any of the other points. So I mean, even if I get down here and look at 1 over 10 to the 10th inside there, there's still a little bit of space around that. So God, I picked a number that's too big for me to even think about. Let's just say like a 10th. So if I go to a 10th here, so we're down here, here's 1/10. The one before that would have been 1/9, and then to the right of that is 1/11. You can just easily construct an interval that doesn't touch either of those points. And we don't need to get into the fancy math as long as you believe that. So none of the points in the set are limit points. Is there a limit point though? 0 is a limit point. It's not in the set, but we have a sequence of points converging to 0. So 0 is actually a limit point. And so here, 0 is the only limit point. This is all part of a thing, a branch of math called topology that we'll actually mess around with as soon as we're done with sequences and subsequences. Questions on that, friends? Because we got to understand the statement of the theorem we're trying to understand the proof of. So that is the theorem that they are going to prove for us. And if you turn over the page, there's a short proof. And then they go back through the history of all this stuff. So we can skip all that. Really, we just go down, they propose a lemma, and then a proof using the lemma. Bye, Anna. See you on Wednesday. So you remember how this works, right? You've got a lemma, and you make lemmas as little tools to prove a bigger result. So our first lemma here is S is a set, and less than or this symbol here, I said it is less than or equal, it's not necessarily that, is a linear order on S. So they're trying to prove a much more general result than we need in this class. So to be a linear order is that you are a generalized version of less than or equal to. And for us, we can simply use less than or equal to for our generalized order. There's other ways to do this, but they're trying to make a much more abstracted statement here. So for us, this is just less than or equal to. Well, what are the properties they're trying to get to? That in the set S, your linear order, if you can compare any two elements in the set, so if this is valid for all x and y in the set, if every point is less than or equal to itself, this is called reflexivity. It's anti-symmetric because just because this happens doesn't mean that this happens, that there's no direct implication of that. There can be, they're equal, but there doesn't have to be. And then transitivity holds, that if x is less than or equal to y, y is less than or equal to z, then x is less than or equal to z. So just some kind of classic properties that you want. In other words, it's this, all the properties of this, but it can apply to things beyond numbers even. Okay, so let's see here. If for every non-empty, so this isn't even the lemma. S is a set, we got the linear order, went off on a tirade there. Then if for all non-empty subsets of S, both the inf of x and the sup of x exist and belong to x, So if that happens, no matter what, so the key here is for all non-empty subsets, that both the infant soup exist and belong to the set, then S is finite. So we haven't quite seen anything exactly like this, but we do know the basics. We understand inf, we understand soup. So let's think about some sets that don't satisfy this property. So for example, X itself, the subset X, could look like this. So X can't be, like say, a closed interval 0 to 1. Right? Because the infant soup do not exist. I mean, they do exist, they're not members of the set, because, let's see here, soup of X equals 1, and that's not an element of X, and the inf of X is equal to 0, and that is not an element of X. So we can't have sets like that if we're assuming this hypothesis here. This hypothesis is really narrowing us down in a strange way. It's saying that we can't have infinite collections of things, really. I mean, obviously it's saying that. But to see that, they actually prove using the contrapositive. So let's take a look at their proof. And this is something I do want to work through together. So by contradiction, we assume S is a set, we have a linear ordering, and we assume S is infinite. And then we're going to show that, you know, we end up with problems like we just had there with that open interval 0 to 1. So the proof by contradiction, we're going to assume, let's see, what are we assuming? X is non-empty, X is infinite, and that we have this linear order. X. And X is, of course, a subset of this. Yes. Okay, gosh, I started reading ahead here. Okay, so take a look at their proof method and see if you can understand it. Look at the next 2 lines, literally just 2 sentences. Draw some pictures and see if you understand what they're getting. I'm going to run to the restroom. guess the other assumption is that the soups actually belong, soup and inf actually belong, we didn't put that. Do we understand the construction? Is that making sense? Are there any troubles? Are you having any, because I had some troubles with this proof. There was a question that I had that I didn't feel like they had addressed. Yeah, Michael.
It's the x sub I part for me. I feel like, so my understanding is correct, you're just choosing random x sub 0 through x sub I, then you're ordering them because of that property, and then you're doing set subtraction.
Kind of. So it's actually a couple of, one of the steps is reversing here. So let's take a look at how we're building the x sub I. And I'll show you where my trouble lies here.
Yeah, also, is S bounded? Because they don't say that.
So not necessarily here. We're not assuming that because we're assuming some other things here. We will assume it's bounded in the actual result itself, but right here, we're not trying to get Bolzano-Weierstrass. We're just trying to get this guy here. So it doesn't have to be bounded in assumption. These kind of do that for us. The fact that the infant soup exists, no matter what, say that it has to be bounded in some way. Does that make sense?
So we're saying that if and soup exists.
Yes.
Okay.
Yes, sir. Yeah, absolutely. Okay, let's go through. So we've got f set s, and then we're going to say for n greater than or equal to 0, we define this recursive sequence. So x sub n is the infimum of s minus all the x sub n's that have come before. So taking that out. What's x sub 0? And that's the problem I had, because you have to initialize this. So if I was reviewing this proof, I would say, but you don't have an initialization for the process. So x sub 0 could just be, and I think this is probably what they want because there's nothing in there at this point, but I think it's just the infimum of s. And I think that makes sense, that we haven't removed anything yet. So x sub 0 is just the inf of s. So let's take a look at what s might look like. Yeah, okay, well, this is, I'm gonna draw these discretely. I'm trying not to draw anything that makes too many assumptions, but I'm not saying that's a finite number of points, but they are discrete, and we'll take a look at the not discrete case in just a second. But right now, if this is s, then this would be x sub 0 right here. Just actually the minimum. And I know that this element, this x sub 0, is actually in s. So one of the things I do know, because of these assumptions that the infant soup are in the set, I know that x sub 0 isn't something like this, that s doesn't look like the open interval 0 to 1, because then this x sub 0 here is not an element of the set. So I know that the point that I'm removing, this infimum, is in the set, And so I'm not dealing with a situation like this, or with a situation like this, where the points are starting to create a limit in that direction. So we don't have anything like this going on. So this is probably one of the better pictures we could have, or maybe even like this. This could work. If I just had the closed interval 0 to 1. That could also work. And then I say, okay, here's the inf, that's x sub 0 right there. So then I take x sub 0 out. Let's go with this picture right here for a minute. I remove x sub 0 and now compute the new inf, right? So x sub 1 equals the inf of s minus that initial point that was in the set, so that has changed things, and we move to the right. And then this would be x sub 1. Yeah? And then you can see here, and I've rigged this. This is rigged to look like what I kind of want it to look like. But this is the picture for me that helped me make sense of this whole thing. And x sub 2, of course, is going to be the inf of s minus x naught, x1, and so on. So that's the basic idea of the construction. Find the inf, take it out, find the new inf, take that out, and the things you're taking out, construe your sequence, or your sequence. Okay, so then we create this new set of those points that we removed. So we say x is the set x of n, where n is greater than or equal to 0. So this is just the sequence of points that we removed. Now here's the line that we need to talk about. Then x of n is a strictly increasing sequence, infinite sequence. Why?
Because you're always taking the smallest remaining thing?
Yes. Yeah, and because the x sub n, there has to be some space between x sub 0 and x sub 1. There has to be a positive distance between these two, because if there wasn't, then I was in this situation here where x sub 0, well, let's go like this. Actually, let's take a look at this. So let's say that's my x. And okay, so what's wrong with that? So infimum of this, let's say that's 0, 1. So here x sub 0 would equal 0. And then if I remove that point, x sub 1 is also 0. And then x sub 2 is also 0. So why is this case ruled out by our assumptions? That's an infinite set.
Because you would contain the sup and inf always in the subset?
Perfect, that's it. Yeah, beautiful. Thank you, Noah. Yeah. So in a set like this, we don't have the property that the sup and inf of every subset are contained, because you can then create these open intervals in there that don't contain their sups and infs. So we can't have this continuous band like this. So yeah, that's absolutely it. So there's no closed intervals in there. There's no open intervals in there. But okay, so why does x1 have to be bigger than x0? So let's see if we can just reason this through. And I had this reason through in my head, I think, yesterday. Now I'm fresh wondering again.
Well, what if x0 is the inf, doesn't have to be the limit? It can't be greater than x.
Yeah, I mean, that sounds right. Yeah. Because x sub 0 was the left end. And if I
In order
remove,
to establish a new inf, you must move
which case x of 1 must be greater than x sub 0.
It sure feels right. That sure feels right. I'm just trying, there's some part of me that's feeling like we need something else. And I agree with all of you, both of you, what you were saying. Let's see. So why can't the sequence be constant? Because, all right, so let's take a look here. So what would happen if x sub 1 was actually equal to x sub 0? Then that would mean that removing x naught didn't change anything. So that x naught,
Well, aren't you,
oh, I think I got it, but yeah, go ahead.
aren't you just taking out every instance of I? Or no?
Yeah, well, yes. So we're basically whittling away from the left. And I think I see now why x sub 0 can't be, oh, here's this, okay. X sub 0 and x sub 1 can't be the same. Let's just argue that, and here's why. If x sub 0 and x sub 1 are the same number, so if x sub 0 is actually the infimum of s minus x sub 0, then x sub 0, then the infimum of the set is not contained in that set. That's the thing, because every set has to contain its own infimum. So if I remove x sub 0 out of it, then x sub 0 can't be the inf of the set because x sub 0 isn't in that set. Does that make sense? If you're not in this set, you can't be its infimum by hypothesis. Okay, I believe this now. I feel pretty good about that. So this can't be, this cannot equal because that would mean that x sub 0, that the inf of some set, some subset, is not contained in the subset. Yeah, that's it. So that means you have to increase. And why do I have to increase? Because I've diminished the set, and we know that as we diminish the set, the inf goes up. So it has to go away. So okay. So I think I buy that. I don't know if you guys buy that or not. Does that sound at least plausible now? Ed? Are you guys okay? Yeah? Okay. All right, good. Are you okay?
Yeah.
Okay, good. So, all right, it's a strictly increasing sequence of members of X. Therefore, its sup cannot be in X. So here's the next thing. So we've got this is a strictly increasing infinite sequence in S. Therefore, the sup of this collection cannot be an element of that collection. Why? Let's draw our pictures. So far, we've got something like this. Here's x sub 0, here's x sub 1, here's x sub 2, and we can even pretend that they're getting closer together. X sub 4. And we know that there's a positive different distance here. How do I know that the sup of this set, so as I come in this way, how do I know that this point, x right here, the sup, is not in the set? What would it mean for that sup to be in the set?
So like x sub n was the sup, then x sub n plus 1 would be not there, which would be wrong.
Perfect. Yeah, exactly. If one of these things actually attains the sup, then the sequence cannot be increasing forever and ever. Does that make sense? we know that this has to, strictly increasing means this. We've established that that has to be the case. If this soup was actually in the set, then that means one of these x sub n's has to equal the soup of x. And from that point, there's nowhere else to go up. That means x sub n plus 1 is x sub n on down the way. Good job, Noah. So that is a contradiction because we have produced a subset that cannot contain its own soup. What caused the contradiction? The assumption that we had an infinite set to begin with. So this caused the contradiction, therefore x has to be finite. And that's the only way this property can hold true. That was a painful long way to get there. But we know that x must be finite. So now once we've got this result, we can go to the big proof. So let's go to the big proof and remember what it is we're trying to prove. So the main theorem was this. Every bounded, so now we got the bounded back in, Noah. Every bounded infinite set of reals has a limit point. So now we go to the proof by contrapositive. So prove contrapositive, i.e. we want to prove that if it does not have a limit point, so S, oh here, let's just go through. So S is a bounded set, subset of the reals with no limit point. And we suppose it is non-empty. So, okay, so this is our big set. And then we take inside here X, it's a subset of S, it is non-empty. Okay, so then the next line is then the inf, oh, okay, yeah. The inf of this set X has to be an X, because if it's not, we can produce a sequence of things converging to the infima. Think of lemma 138. If your inf isn't in your set, you could always get a sequence of points converging to it. So this inf has to be in there, otherwise we can produce a sequence converging to the infima of X. And that would mean that this is a limit point, i.e. inf of X is a limit point. And we've just said this set has no limit points. So that is, now we've actually reached the contra positive, right? That if we have a bounded subset with, wait a minute, what the hell did I just say? With no, what the fuck am I doing? Hold on, I've got myself completely confused. Okay, hold on. So the contrapositive of the Bolzano-Weierstrass is, if we do not have a limit point, if there's no limit points, then the set must be finite. Okay, so we're assuming we have no limit point. Oh, okay. Okay, got it here. Oh, okay, we're getting ready to apply the lemma. That's what's going on. So we are getting ready to apply lemma 1. That says that if the infant soup of every subset are contained in that subset, then the set is finite. There we go. Okay. So, have I lost you? Hopefully not. I can see why you'd be pretty vegged out by this, but let's just finish it up since we started. So the inf of x in the subset, this arbitrary subset, must be in there, because if it's not, we can produce a sequence converging to the infimum. Something like this. And that would make the infimum a limit point, because every neighborhood of it would contain some part of that sequence. So, yeah, so that can't happen. So, so this has to be the case, because if it's not, then we have a limit point. Similarly, the sup of x has to be an element of x, because if it's not, you've got a sequence of points converging to that sup in some situation like this, where 1 is your sup, but it's not in there. So, what we have is that for every non-empty subset of S, the inf and the sup belong to that set by lemma 1. X must be finite. And that gets us our contrapositive. Not this implies not that. That was a lot more painful than I imagined it being, but I thought let's do some math that's not in our book. Okay, good news. You don't need to know that proof. Yes, my friend, yes.
Can I just double check this last
Please.
piece on the right side?
Yeah.
I followed you all through the inf stuff, and then when we
That's
started
amazing.
talking about the soup,
Yes.
I understand that x must be finite. Can I just get a reiteration of why we know that the soup is not? Or that the
Got it. Yeah. Oh,
that
this
makes
this
sense?
over here.
Yeah.
Yes. So are you cool with that? We produce this increasing sequence by taking the inf and then removing
Yeah.
the inf. Cool. So if the sup is actually in this set, so let's say the sup of this collection, this sequence, is in the set. So that means this sup coming in this way actually must be equal to one of the points in that set. But that means there's nowhere else to go up.
Okay.
So the sequence couldn't ever keep increasing.
Okay.
Does that make sense?
Yeah.
Yeah, I think I understand it now too. Okay, we're not done. Any other questions? Thank you, Kayla. Thank you for caring, Kayla. It really means a lot. Let's actually go back to a problem I left with you guys. Did anybody come up with a sequence that had subsequences converging to every real number? Okay, let's start off with a chiller. Let's go back to that, but let's do a chiller example. So I actually wanted to work through one of the problems in the book, and that is 251. Problem 251. Instead of it being homework, I want to do it together. So this is 251. Give an example or argue that it is impossible. So let's actually just go through this. A sequence that has a subsequence that is bounded but contains no convergent subsequence. Can we produce this, or is this impossible? And let's keep Bolzano-Weierstrass up here. So Bolzano-Weierstrass, that's going to be the thing that helps us answer all these questions. If so every bounded sequence contains a convergent subsequence. That's Bolzano-Weierstrass. Does that have any bearing here? You say, now Michael's giving a thumbs down. Why is that?
Because it's a subsequence that is bounded, like it means that's like the exact same wording as that, just small sequence of subsequence.
That's brilliant. Yeah, a subsequence is still a sequence. So
if you have a sequence that has a subsequence that is bounded, this is actually a bounded sequence, if you forget about where it came from.
So it has to contain a convergent subsequence.
Yeah, very nice, yeah, exactly. So our answer here is gonna be, because a subsequence is still a sequence, if it's bounded, it must contain a convergent subsequence. Good eye on that.
Cool. So I was knocked out. Nice. If there's any questions, of course, let me know too. That doesn't make sense to you. Then part B, a sequence that does not contain 0 or 1. Sequence does not contain 0 or 1 as a term, but contains subsequences converging to each.
We'll build ourselves up to the big problem.
Oh, yeah, let me take a look. Yeah, and then, exactly, yeah, perfect. Maybe you should check out the next ones, Michael. Just start on them.
Did I give you a Dropbox to turn in?
Okay, cool. Okay, awesome, cool, awesome. I knew you did it. I wasn't doubting that in the least. I was just like, did I give you a place to turn it in? Okay. I figured you would have asked, but I just wanted to be sure. Next one's up. Have you gotten the second one, Michael, or the third one?
I feel like it's the same kind of thing, you just like make one that does each one and then to read them, but I'm just having a hard time thinking of a generic one that converges to each one.
There lies the challenge, yes. See, you dressed up today too. You know, you're on the same wavelength. You got some. It's okay. This is good. This is good thinking, though. That is absolutely essential what you're doing there.
So you've got one conversion sequence. How do you put that together? How do you convince the two?
So what's stumping you here? Yeah, fair enough. Okay, that's cool. You have your space because I know what you're going through. Kind of. Vaguely. I've got problems of my own, is all I'm saying. You got that one?
Yeah, it hasn't been sequence, I'm just trying to find a way.
Oh, you're getting fans. Okay, cool.
It's okay, it's really okay.
So then we could do something like, what's the one, so it would be like 1 over n. And
Yeah,
then
that's a good one.
approach to 0.
Yeah.
And then we could do, what's the, from 0 to 1, so it would be, what's the,
So you could do 1 minus 1 over n, or 1 plus 1 over n. 1 comes into 1 from the left.
Okay.
Does that make sense?
yeah.
And so that's a real easy way to construct. Just take the number you want to converge to and add 1
Yeah.
over n to it or subtract that.
Okay,
Yeah.
just because I was thinking like, this guy has to be within, or I could come from
Yeah,
this
it totally
way.
is okay.
Oh,
Yeah, yeah.
okay, cool.
Yeah, yeah. Is that, okay, yeah, yep.
Perfect.
Okay.
Thank
You're welcome. Yes, sir. I'm more curious to see what you have to say for D.
So,
Oh,
For
which one
each
is
one.
this?
so for each one, I'm doing n over like something, n plus 1, so that'll do a half. The third, that'll do a
Oh.
third.
Cool, okay, yeah,
You
I
see
like
one,
that. I like that.
limits, yeah.
Yeah, that's pretty cool. Yeah, yeah.
Easy to do the hard thing. Right.
Oh, good work. Question D is like the serious challenge of all of them. They're all good, but then D really pushes it. I don't want to take it. Would it be okay if we went through? Is it okay? I don't want to take any joy from anyone. So like this one, remember the key here, friends, when you want to build sequences that have your subsequences of whatever flavor, interleaving. So first I get a sequence that converges to 0. A good old 1 over n. All right, so that converges to 0. That's great. And then to converge to 1, I like to do 1 minus 1 over n. So 0, 1 half. I'm literally taking 1 minus each of these numbers. And that converges to 1. And then just alternate these terms. Oh, did I do something wrong?
We just gotta get rid of 0 and 1.
Oh,
Which I
oh,
think
you
are
don't
starting
necessarily, no,
points.
why do you think, that's curious, why do you think that?
Oh, I thought it just says that does not contain 0 or 1.
Oh, you're right. Oh, is that, okay, thanks, Michael. You say that because you read things and
We
comprehend.
just gotta change this.
And comprehend things, so yeah, that's my problem. Thank you, sir. Yeah, so then we can just interleave these. You can just go 1 half, 1 half, 1/3, 2/3, 1/4, 3/4, on down the way. And it's gonna look weird, but each of these sequences is now a subsequence of this sequence. It has to be, right? Like there's no question about it. So we have satisfied the request. And then when we come over here to do all of the 1 over n, so I want infinitely many subsequences in here, I'm going to play the same game. I'm going to first come up with a sequence that converges to 1. Does this one also say doesn't have? Okay, thank God. All right, good. All right, good. All right, so for this one, first I get a sequence that converges to 1. And check this out. Since it doesn't forbid 1, why not? Since it doesn't forbid a half. Oh, hell yeah. Now, so each of these sequences, that converges to 1, that converges to a half, that converges to a third, you see how that game's gonna go. But how do I interleave them? That's just like the Cantor proof, right? The Cantor diagonal. So here's the interleaving strategy. And I've just got them all lined up. I just wove infinitely many things together into a sequence that now contains, and so you have to kind of explain all that. That's painful. And that might have been what you were trying to do, Noah. I'm not sure. I know Michael was
giving it his damnedest.
Well, I was thinking about that for like the challenge one. If you could do every rational number, then couldn't you?
That's it.
Yeah.
Yeah, that's it.
Well, the issue would be proving that it goes to any irrational number, I guess? Wouldn't it?
Yeah, yes, so, but then, so let's talk about that. So the challenge problem was, now make a sequence that contains subsequences converging to every real number. It will suffice to do one that converges to every rational. Let me explain why. So this is like, I don't know what this is. This is like C prime or something. A sequence with subsequences converging to every real number. So what we actually do first is what seems like a lesser request. So here we're going to have a sequence with subsequences converging to every rational. And once we have that, you can approximate any real with a sequence of rationals. And so that sequence of approximations will live in this world that we just create here. And you can find subsequences go wherever you want. So here's what I first do is, we can list the rationals because it's countable. So we say Q is going to be Q1, Q2, Q3, Q4, on down. And then I'm going to do this game over here. I'm going to list the rationals Q1, 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 on down, Q2, Q2, on down, and you see the game here. I just want to make enough so I can make some diagonals. And then zip them together, a la Cantor. And now this sequence, certainly you would agree that this sequence contains subsequences converging to any rational inside of it. Does that make sense?
Well,
Yes. Please.
yeah, but couldn't you just do the one where you just list every rational and then that would do it automatically maybe? That's what I was thinking.
No, because, so that, I like the way you're thinking. The problem with that is, so if I have Q1, just take this list. I think this is what you're saying, right, Noah? So take my list of rationals. So where is the subsequence? So an infinite chain of things converging to Q5. Well, I know that Q5 is in there, right? But that's just one. What's the next element in this sequence?
Arbitrary?
And it's arbitrary, and it might exist, right? And it probably does exist, something that's close to this, but this makes it solid here. Over here, I don't know for sure that I can create that sequence, but here I definitely see it laid out. So I think, Noah, that might work, but I don't know how to argue that it works. But I can argue that this works. So that's why I go that route. Yes, ma'am.
So if you're writing a proof by construction, how do you say, like, how would you indicate that, like, that pattern continues infinitely?
Yeah, that's tough. I think we'd have to look at what Cantor did
Okay,
and see how that, but I mean, drawing a picture like this,
yeah.
just some fancy latex, it's all good.
Okay.
Yeah, exactly. I think literally showing that scheme would suffice.
Oh, okay. I
Yeah,
just
yeah.
didn't know if that counted or not.
Yeah, I think it does count.
That's super cool.
But now this sequence contains a subsequence that converges to any real number. So you give me a real number, let's say pi here. Where's the sequence that converges to pi? Well, I know that pi can be approximated with this sequence. So there's a sequence that's getting closer and closer to pi. And inside of here, all of those numbers exist. Don't they? Each one of those numbers exists in here because they're rational numbers, and we've got them all in here infinitely many times over. So that sequence is in here as a subsequence, and that sequence converges to pi. So once you've got this thing, you've got everything. Yes, sir?
So the whole crazy part before break that you were saying is we're able to use a countable thing to construct non-countable things?
Yeah.
Uh,
It's I know. It's crazy. It is. That's why it's just I love it because it's just so counterintuitive and baffling. But. So let's take a look. Now, thinking about this might actually give us a little leverage on the very last question. So 251D says a sequence so 251D is a lot like C, except they say, but make sure there's no subsequences converging out to points outside that set. So over here, subsequences converging to each of these and only these. And no other points. Is that possible? And you should probably suspect it's not, just by all the things that I'm saying and the order of these questions. Why is that not possible? Is pi in this sequence? But there's things converging to pi here. What is something that we could converge to in that sequence over there that isn't in that set? It's just not fans, it's not pi. 0. Right? In fact, here's the subsequence that converges to 0. Write down any one of these. So it's impossible because as soon as you've got subsequences converging to any of these things, you've got subsequences converging to where they converge as well. So that is an impossible request. It's certainly a good place to end the day.
Yeah.
Yes, sir.
Go on, like the time before when you gave out homework or whatever, would you have like homework 3 of mine, or is it somewhere?
Oh, yeah, let me see if you didn't get it back? Is that what
Yeah.
happened?
I missed it.
Yeah, let me take a look.